Okay, so I'll be talking about this very old problem called Fermi-Pasta-Ulam and Singhau problem. So, I mean, for a long time it was called FPU, but then people realized that this person called Mary Singhau actually did all the simulations, and at that time people didn't, I mean, simulations were not serious, so they didn't include, but now it's called FPUT problem, that's what I'll call it. Okay, so this work is done with my student Santosh and colleague at ICTS, Amit Apte. Santosh is here and maybe he has a poster, maybe not, I don't know. Maybe he's not here, okay. Okay, so, and there's an archive paper here. Okay, so what is the problem? I mean, so basic question is how do purely Hamiltonian systems equilibrate? And then underlying question is why does statistical mechanics work? So this is what they wanted to check, and what they did was you take an harmonic chain of particles and which is described by some Hamiltonian like that. So each particle has a position qi and a momentum pi, and there's a kinetic energy, and then there's an interaction part, just nearest neighbor interactions, and so this is a quadratic part, and then there's so this is just a harmonic chain, and then you add some nonlinear terms. Okay, so you can add a cubic and then fourth power and so on. But this is the simplest, and today I'll just talk about the cubic model. Okay, so of course, if there's a cubic part, then one is worried that it's not stable and so on. But if you have a cubic potential, if the energy is kind of small, then it's a bounded system, so there's no problem. Okay, and we always work with constant energy systems, so it's okay to have a cubic term in the interactions. So E is the total energy divided by number of particles. So that's one quantity that is a parameter. And actually, if you look at this system, I mean, the only relevant parameter is, okay, so there's this enharmonicity and there's this energy. But finally, you can show that what is relevant is for our like discussion of thermalization is this parameter, okay, so it should be the other way around. I have written it here. The strength of the enharmonic energy versus the harmonic energy, okay. So it should be inverse of this. Alpha x cube is the enharmonic energy and mu x square is the harmonic energy of each spring. And what we want is that for small nonlinearity, which means the energy in the enharmonic part is kind of small, then we want to ask, do you still get thermal equilibration? Okay. So this parameter is then given by this constant alpha times energy to the power half by the spring constant to the power 3/2. So this is a dimensionless number. And this and the system size, they are the only dimensionless parameters that are relevant. Okay, so now the usual expectation is that, okay, if you don't have enharmonicity, then this is a integrable model. You can decouple, write it as a bunch of independent oscillators and show there should be no thermal equilibration. If you switch on any interactions which is given by this epsilon, it should thermalize. So how do we verify this? And this is what if you wanted to do. Okay, so so let me just say that you can go to a new set of coordinates by linear transformation. These are called normal mode coordinates, and in this normal mode variables, which is just a linear transformation, the Hamiltonian is this the harmonic part with just a bunch of independent oscillators with different frequencies, and then there is some interaction between the different modes. Right, so so if you like if I start from some initial condition and then let the system evolve, then what I expect from equipartition is that eventually I should get some sort of equipartition, which means that all modes should have the same energy. Okay, so each mode energy is basically the energy of the oscillator. And in this system, if I want to test equipartition or equilibration, I should check that every mode has roughly the same energy, right? So here, because the enharmonic part has a small parameter, I can neglect the contribution of the enharmonic energy when I look at equipartition. Okay, so it's okay. So this is exactly what Fermi-Pasta et al. Tried to do. They put for a small nonlinearity, which is like 0.01 and 32 particles. So initially they put all the energy in just one of the modes out of these 32 modes, and then you try to see what happens at long times. And what they saw was something like this. So this is from their original paper. This is energy of each mode versus time. And initially, all the energy is in just this one single mode, which is the one of the longest wavelength mode in the system. And all the other modes have zero energy. And with time, what they saw is that, okay, so initially it seems they are all kind of interacting and mixing up. But actually only like the very few of the modes get excited, and then after some time you find that you almost get back to the original state. Okay, so you don't get what you were expecting. So the other thing that you might want to do is, okay, so this is just one, you are starting from one initial conditions and looking at the energy of each mode. Maybe it makes sense to kind of do a time average over, or like a running time average of the energy of each mode, and ask, do we get equipartition? And in that case also they see that they don't see any equipartition. Okay, so so main conclusion was equipartition is not achieved, and so then 65 years, this was 65 years back, and mostly, I mean, people would have imagined that this must be now understood. Okay, but so in last few years there have been some new developments, and so there has been a claim that in this paper, so route to thermalization in the alpha FPU system, and then there's this other more recent paper. And the main thing that what these papers claims is that if you, FPUT had not waited long enough. If you really wait for long enough, the system will eventually relax, okay, for any system size. And they have a theory which basically says, okay, so here's the model. So you have the harmonic part and then interactions between these harmonic parts. And the theory basically looks at the resonance between these modes. And then the prediction is that if you have to go to like high order perturbation theory, and then you can identify resonances, and this leads to equilibration, and they make a very specific prediction of the time it takes to equilibrate. Okay, so how long do you have to run the simulation before you see that all the modes have the same energy? And they have this prediction that it goes as a very large inverse power of the nonlinearity. Okay, so if like for FPU epsilon was like 10 to the power minus 2, so this is really huge, right? So that's why they didn't see equipartition, but if you actually you can see. So in this paper they also do numerical studies and they verify this. So one of the things they do in the simulations is that you don't start from one initial condition. So because if you start from one initial condition, you can never see any equilibration. Okay, so you'll always see that things are just fluctuating all the time. So you have to do some sort of averaging. You can do either a time average or you can do an ensemble over initial conditions. So in this paper, what they do is they do an average over a set of initial conditions, which is on, so the initial conditions is on this energy surface of this 32 into 264 in dimensional phase space, but you take a tiny blob on this phase space, okay, initially, and then you let all those points evolve and do an average over that initial blob. So that there's some initial condition over which this averaging is done. And then they basically look at equipartition of the normal modes of the okay. So now what we have done, they verified this particular in their simulations. So in our studies, what we have done is we look at equipartition in real space instead of normal mode space. That seems a more natural thing. For example, I just look at kinetic energy of each particle. Has it reached thermal equilibrium, right? So that's the easier thing to look at. And this is something which works even at large nonlinearity, which is something that won't work for normal mode energies. And the other question that we ask is, if you do a time average versus this ensemble average, do you get different results? What is this choice of this initial ensemble, how does it affect results? And then we ask how is this related to chaos and integrability of the system? Okay, so we the results on FPU, TODA, and harmonic. Okay, so these are let me just show you the results. Okay, so we have this chain, and initially what we do is put initial conditions like maybe a few oscillators have a lot of energy, all the others are at rest. So this is like the various 32 oscillators, and this is kinetic energy. So initial condition is like this: only the few guys have some energy, and everything is at zero energy. Then at time 500, you get something, maybe this thing, and then at 1000 you get something. So the energy is like doing something, and at very long times you find that you get equipartition. Okay, so that's at like 10 to the power 4th, sometime like that. Okay, now you can also look at like the energy of, sorry, this one, of various particles as a function of time. And again, so initially only a few particles have a lot of energy, and most of them are zero. And you again average over some very small tiny blob in phase space, okay, and then you find that you get equilibration time scale. Okay, so now the main result that we find is that the time scale from here, okay, so you'd say like at maybe it's 2.5 in 10 to the power 4 things have reached thermal equilibrium. But when you look at normal modes, you find that it's a much larger time scale. Okay, so that real space equilibration happens at much shorter time scales. So this is like equilibration time plotted versus the nonlinearity parameter. This is what you would get from normal modes, and this has this 1 by epsilon to the power 8 slope. But for real space equipartition, it has different slope, and this slope goes from between 4 to 6, and the slope changes with the spread in initial conditions. Okay, so basically like so you have this big phase space, and initially you are not starting from one point, but you are starting from a small blob, and this blob has a size gamma. And for different gamma, so gamma can be really small, okay, like even 10 to the power minus 8 is sufficient to eventually equilibrate the system. But then some details change, okay, this particular, the slope that you get out here, it changes with gamma. Okay, so the other result is like if you do a time averaging, then you get completely different results. I'll take 1 minute maybe. So even after very like much larger times, you don't get equipartition if you do this running time average starting from just one initial conditions. Okay, then this role of integrability, if we do the same experiment with integrable system like a harmonic chain or a Toda chain, you find that the harmonic chain doesn't equilibrate, but the Toda chain does equilibrate. Again, given provided that you start from this, if you start from a single point, of course it doesn't, but if you have this tiny blob, that's sufficient to equilibrate the system. Okay, and this we can understand from the fact that if you ask like how does this blob spread in time, so in a chaotic system, of course, like different points will spread out exponentially. In a harmonic chain, it turns out that you can show easily that the blob just doesn't spread at all. But in Toda, even though it's an integrable system, it spreads linearly. Okay, it's not exponential growth, but it's a linear growth. Okay, these are some plots to verify that. But that's the reason that eventually, I mean, you start from a blob and it spreads over the entire phase space, and that's why you get equilibration. Okay, so the summary is that, okay, so I've just written it, and I'll just say that this present study is relevant for thermalization in small systems. For macroscopic systems, at least we believe that ergodicity, which is relevant here, is kind of irrelevant for macroscopic systems. And statistical mechanics works probably because of coarse graining and something called typicality. Okay, so I'll just stop.